Space is vast and mysterious, but it's not empty. Scattered across the cosmos are enormous clouds of gas and dust. We call these nebulae. These nebulae are like cosmic kitchens. They're where the ingredients for stars, planets, and even life itself are mixed together. These nebulae are mostly made of hydrogen and helium, the simplest elements in the universe. There are also traces of other elements like oxygen, carbon, and iron. These heavier elements were forged in the hearts of long-dead stars. When these stars exploded, they scattered their guts across the cosmos. This cosmic dust is what seeds the nebulae, enriching them for future generations of stars and planets. Inside these nebulae, gravity is constantly at work. It pulls the gas and dust together, like a cosmic sculptor. Over millions of years, these clouds begin to clump together. As these clumps grow larger, their gravity gets stronger. They pull in even more gas and dust. The heart of these collapsing clouds gets denser and hotter. Temperatures soar to millions of degrees. This intense heat and pressure trigger nuclear fusion. Hydrogen atoms smash together, fusing into helium and releasing tremendous energy. And just like that, a star is born, blazing with light and heat. The birth of a star is a dramatic event, but it's not the end of the story. In fact, it's just the beginning. As a star ignites, it blasts out powerful winds and radiation. This stellar wind pushes away some of the remaining gas and dust, but not all of it. Some of the material remains bound to the newborn star by gravity. This material, a swirling disk of gas and dust, is called a protoplanetary disk. It's within these disks that planets will eventually form. Imagine a spinning figure skater, arms outstretched. As they pull their arms in, they spin faster and faster. The same principle applies to the protoplanetary disk. As gravity pulls the material inward, the disk spins faster, flattening into a pancake shape. The inner part of the disk is hot. It's constantly bombarded by radiation from the newborn star, but the outer regions are much cooler. This temperature difference plays a crucial role in the types of planets that form. The protoplanetary disk is a chaotic place. Particles of dust and ice are constantly colliding. Most of these collisions are destructive, but some collisions are constructive. These particles stick together, forming larger and larger clumps. This process, called accretion, is the first step in planet formation. Imagine a speck of dust, smaller than a grain of sand, floating in the protoplanetary disk. It's surrounded by billions of other dust particles. They're all moving at different speeds, bumping into each other. Most of these collisions are glancing blows. The particles bounce off each other and continue on their merry way. But sometimes, just sometimes, two particles collide head-on. They stick together, bound by static electricity. This new, slightly larger particle continues to drift through the disk, colliding with other particles. Some stick, some don't. But over time, this particle grows larger and larger. This process, called accretion, is how planets begin their lives. It's a slow and gradual process taking place over millions of years, but eventually these tiny dust grains grow into larger clumps, then pebbles, then boulders. And as they get bigger, their gravity gets stronger. The stronger gravity attracts even more particles, accelerating the accretion process. It's like a snowball rolling down a hill, getting bigger and bigger as it goes. Eventually, these growing clumps become large enough to be considered planetesimals, the building blocks of planets. The protoplanetary disk is a crowded place. Thousands, maybe even millions of planetesimals are swirling around the star. They're all vying for the same material, the same space. And as they orbit the star, their paths cross. Sometimes these crossings result in catastrophic collisions. Planetesimals smash into each other at incredible speeds, shattering into countless pieces. It's a cosmic demolition derby. But other times, something more graceful occurs. Two planetesimals, drawn together by gravity, gently nudge each other, altering their orbits. They may become gravitationally bound, orbiting each other like a miniature solar system. These gravitational interactions play a crucial role in planet formation. They determine the final architecture of the solar system, the number and size of the planets, and their orbital distances. It's a delicate dance, choreographed by gravity. As planetesimals continue to collide and merge, they grow larger and larger, eventually becoming protoplanets. These protoplanets are the precursors to full-fledged planets. They're still growing, still accreting material from the surrounding disk, but they're well on their way to becoming the celestial bodies we know and love. Section 5. A star is born, a disk is formed, the protoplanetary disk. The protoplanetary disk is more than just a birthplace for planets. It's a dynamic and evolving environment, shaped by the interplay of gravity, radiation, and magnetic fields. It's a crucible where the raw materials of the universe are transformed into the building blocks of worlds. The disk's structure is not uniform. It's characterized by rings, gaps, and spirals, sculpted by the gravitational influence of the forming planets. These features provide valuable clues about the processes that govern planet formation. The composition of the disk also varies with distance from the star. The inner regions are dominated by rocky materials, while the outer regions are richer in volatile compounds like water ice, methane, and ammonia. This difference in composition is reflected in the types of planets that form. The protoplanetary disk is a place of intense activity. It's a cosmic construction site where planets are assembled from the bottom up, brick by cosmic brick. It's a testament to the power of gravity, the elegance of natural processes, and the boundless creativity of the universe. Section 6. Gravity's Dance, Shaping the Planetary Ballet. As protoplanets orbit within the disk, they exert their own gravitational pull. This pull influences the orbits of smaller objects, drawing them into a cosmic dance. This dance, orchestrated by gravity, determines the final arrangement of planets within the emerging solar system. Picture a protoplanet, a nascent Jupiter, circling the central star. Its gravity acts as a shepherd, corralling smaller planetesimals and protoplanets. Some are drawn into its embrace, becoming moons or merging with the growing giant. Other objects are flung outward, cast away from the gravitational well of the giant. This gravitational interplay sculpts the protoplanetary disk, clearing gaps and creating rings. It's a cosmic ballet, a delicate interplay of forces shaping the destiny of worlds. The dance of gravity is not limited to individual protoplanets. The entire disk is engaged in a complex gravitational interplay. This interplay can lead to orbital resonances, where the orbital periods of two or more planets are related by a simple ratio. These resonances, like the harmonious notes in a symphony, can stabilize the orbits of planets, preventing them from colliding or being ejected from the system. It's a testament to the elegance and order that can emerge from the chaos of planet formation. Section 7. From the inside out, a planet finds its layers. As protoplanets continue to grow, their interiors heat up. This heat comes from a variety of sources: the decay of radioactive elements, the heat of accretion, and the gravitational pressure of the planet's own mass. As the interior heats up, the materials inside the protoplanet begin to melt. The heavier elements, like iron and nickel, sink towards the center, forming a dense core. Lighter elements, like silicon and oxygen, rise towards the surface, forming a mantle. This process, called differentiation, is what gives planets their layered structure. It's like separating oil and water, with the heavier elements sinking to the bottom and the lighter elements rising to the top. Differentiation is a crucial step in planet formation. It's what allows planets to develop magnetic fields, which protect their atmospheres from being stripped away by the solar wind. It's also what allows planets to have active geology like volcanoes and earthquakes. Section 8. A solar system emerges, a symphony of celestial bodies. Over millions of years, the protoplanetary disk dissipates. The remaining gas and dust are blown away by the stellar wind or accreted onto the central star. What remains is a fully formed solar system, a testament to the power of gravity and the elegance of natural processes. At the center of this solar system is a star, the engine that drives the entire system. Orbiting the star are planets, each with its own unique characteristics. Some planets are small and rocky, like our own Earth. Others are gas giants, like Jupiter and Saturn, with massive atmospheres and dozens of moons. The specific characteristics of a solar system depend on a variety of factors, including the mass of the central star, the composition of the protoplanetary disk, and the gravitational interactions between the forming planets. But despite these variations, all solar systems share one thing in common. They are born from the collapse of a giant molecular cloud. The formation of a solar system is a complex and wondrous process, spanning millions of years and involving a delicate interplay of physical forces. It's a testament to the boundless creativity of the universe and the elegant laws that govern its evolution. Section 9. Cosmic Wonders Unveiled, Reflections on the Grand Scheme. The study of planet formation is more than just an academic pursuit. It's a journey of discovery that deepens our understanding of our place in the universe. By studying how planets form, we gain insights into the history of our own solar system and the conditions that led to the emergence of life on Earth. We are still in the early stages of understanding planet formation. New discoveries are being made all the time, thanks to powerful telescopes and sophisticated computer simulations. As we continue to explore the cosmos, we are sure to uncover even more wonders about the processes that govern the birth of planets and the evolution of solar systems. The next time you look up at the night sky, take a moment to appreciate the vastness and complexity of the universe around us. Every star you see is a potential sun, orbited by planets that may harbor life. And every one of those planets was once just a swirling cloud of gas and dust, shaped by the same forces that gave birth to our own solar system.